Okay, so here's some brainstorming about Penumbra. So for context, for people who are not, already, all on top of my specific project, Penumbra is a private proof of stake L1 that provides an interchain shielded pool. So you can take any asset from any IBC connected chain, move it in. It has a Zcash style shielded pool, and it also has an on-chain DEX. So you can do on-chain trading with private strategies. The model is basically that the DEX activity in aggregate is public state, but each user's set of positions is private state. And probably in contrast to everything else that's discussed here, this is like an entirely ZK-based design. So we have a strict separation conceptually between private user data and public shared state. And we do all of the proving client side and sync all of the end user data only onto end user devices. So yeah, like I said, if you start with Zcash, add multi-asset support, add proof of stake, add cross-chain drop, and add a DEX, you get Penumbra. So the performance right now is like acceptable, I would say. You can do client-side proving for normal transaction in probably about 10 seconds on a MacBook. The overwhelming majority of that actually is like browser overhead, because there's a whole team at Google that's dedicated to like making your life as an extension developer worse. And so you have to work around that. If we were running native code, it would actually be 700 milliseconds, which is incredibly frustrating, but like that's, the way it is. And so a thing that I'm interested in kind of brainstorming about, if anybody has ideas, is what are ways that we can kind of compose TEs back on top of this in order to improve UX. And this is kind of different, I think, than a lot of that exists, like the other stuff that's going on in the space, because we're not starting with here's this thing and we're trying to make it trustworthy using a TE. We have a system where all of the trust in everybody else's actions in the system is actually already being provided by the ZK proofs, but we somehow have this like last mile problem of, maybe it can work in a web browser on like a MacBook, but if you're on like a, worse laptop, it's like too bad to use. Or maybe you have like really constrained, data connection or something like that. And so how do you have these kind of like personal applications of TEs that can serve specific users rather than trying to serve an entire protocol? So I'm gonna show you, here's a slide that kind of shows the overall like state model, right? For shielded transactions, you have a ZK proof that's providing trust. There's some commitments to like new output states. You have a way to mark privately that some input state was consumed. And you have some encryption of here's the kind of actual data of my transaction that you're going to encrypt to yourself and use basically the chain as your own little DA layer. And so the big challenge here is that now every user, sort of all of their transactions are their own little micro rollups, and now they have to manage all of that state, because we've like solved privacy by eliminating the like big database in the sky that you could just query. And now you have to do that. There's a lot of focus on client-side proving, but compared to proving, compared to client-side state management, proving is actually very simple, because you just like get, a few people to like make an optimized thing, whatever, you're done. It's managing the state that is the challenge. What is the state that you actually have to manage in this type of ZK system? Basically, you have this interesting sort of role inversion of a Merkle tree. Rather than the sort of big Merkle tree living on a full node on the big server and then using auth paths to convince clients that their query was correctly answered. In this ZK setting, you're using the Merkle tree to allow a client to prove to the chain and thereby all the other participants that their state was previously included. And on the slide that I just had about the state model, nothing in that is identifying which user is making which transaction. And that's a core part of the privacy, the anonymity, but it means that there's a problem that the client has to figure out, A, like which fragments of encrypted state are relevant to me, and then B, how do I maintain the Merkle paths that witness that those specific states were included up to the state root. And once I figured out, hey, these two specific pieces of data are relevant to my my account, my wallet, other people are going to keep making transactions. And as they do that, that's going to change the Merkle tree. And I have to synchronize that as well. So I'm going to get new auth paths as new stuff happens. And you really don't want to have every client have to process every transaction. So what we did at the protocol level to avoid that is we have a scanning system with optionally delegated detection. So every wallet has to embed basically this like ultralight node that scans and synchronizes this filtered view of the chain state. And built into every address, there's like a special subkey called a clue key that allows people to make these sort of, it's basically an encrypted Bloom filter. And you can hand out a detection key to some untrusted third party, and they can probabilistically filter all of the transactions and give you basically a subset that will have all the ones that are relevant to you. But there's still some idea of, exactly how, could they collect a bunch of those over time, et cetera. So that's, I'll get to there. That's one area where TEs might be useful. For the tree sync, we have a cool Merkle tree that's like not super, relevant to get into, but basically you can very efficiently discard and filter and skip over stuff while you're updating it. And so this is kind of our idea is like if you have the ability to delegate detection of which transactions are yours, and you have the ability to fast forward over other people's state updates, then maybe that's enough to get like a really scalable private client. So that's kind of the protocol level support. That's the foundation that we can now layer TEs on top of. The other challenge is front ends for private chains. What does that look like? And again, trying to build everything without having to rely on a TE as like a load-bearing component. We have on the web, which is sort of the most open type of thing. We have this architecture where inside of the browser extension, which is having the user's wallet, we have this concept of like a view service, which is basically like your local RPC that has your personal indexer, et cetera. And it synchronizes your private state. So that view service then can do selective disclosure of transaction contents to some website that you allow. And the website can propose some transactions, and you as a user can approve that or not. So there's a few notes here. One is that like this already means that we don't have to like leave any or take any keys out of the extension. And the sync is shared. The effort of doing synchronization is amortized over all the front ends that a user might want to use. This part is not super related, but basically this is kind of the TE-less architecture of let's put everything on the client and then here's how we're going to do it. And then now we have issues where you have all this stuff on the client So a few ideas, which I guess like this list is like slightly half finished. One is like, what if you offload the entire view service functionality into some kind of personal TE that's hosted by the user? And two big challenges that show up for that are, number one, it's not very resource intensive, but it's not completely free. So there's some cost to run this view service, and that needs to be paid for. And because it's anonymous, there's not really some kind of on-chain metric that you can look at to be like, is this wallet real or is it a sybil? Like the whole point is that there's no data on chain. And so you actually have to pay for things and have an economic model. But what does that model look like? How do you have some kind of like sort of system of like a marketplace of like that just allows a user to like pay a small amount of tokens periodically and have their data solved? But then there's this kind of awkward cold start issue, which is if you're trying to do anonymous payments using the anonymous payment system, and in order to synchronize the anonymous payment system, you have to like first have your data. That's kind of awkward. And then a second idea is, what if you tried to offload only this like fuzzy detection part and have someone run that as a service? And then maybe it doesn't have to be sort of a user's personal thing because there's already a cryptographic guarantee that you're not leaking a lot of metadata. One idea for the cold start issue, separately to the idea of using TEs, is there's a really cool idea called DAG sync, which is basically like once you know about one of your transactions, you can check whether the outputs are already spent. And if they're not, then you have spendable funds. And if they are, you can query what is the transaction that spent them and kind of follow the chain of your own UTXOs out to the current frontier. So one idea is that we could use the detection system as basically a way for a client to find an entry point, but then you run back into this. Either you need to have a economic model with a market, or you need to have a centrally run service with a central planner that can prevent resource abuse. And that seems very hard for a privacy system, both because the data is supposed to be private, and also because you really want to avoid running services, right? So for instance, with Penumbra, the whole thing is designed so that there's no back-end infrastructure, and like Penumbra Labs just does software development and there's no servers running anywhere. But yeah, that's kind of some brain dump of interesting challenges of like, how do you allow per user TEs that can kind of offload some of this work, but where that TE is basically treated as an extension of the user, and they can fund that anonymously or not have to depend on a specific centralized provider. And I don't know the answers to those things, so curious what other people's thoughts are.
Just really interesting. It seems like similar problems to Monero. Like Monero had like all of these same problems, and you've got like much more complicated versions of the same problems because you're doing more complicated stuff with the chain.
Yeah.
Or DAG sync, you have to like query a node based on the tags you get, right?
Yeah.
Do you also have to use some kind of a mixnet like solution on top,
or you could just give up? Yeah. I mean, or maybe you query from a TE. But
so you run a Penumbra node inside a TE there?
Or some kind of indexer.
Right. Okay.
Yeah.
Yeah.
I was wondering, is this like TE extension necessary for the users?
No. And it's an important design sort of principle that like as a user, I'd never have to like I can be the like, you know, mountain man, like running my stuff like entirely locally in my cabin, and it's slow, and that's fine. It's just once you've got there, like now how do we make the experience suck less?
Any other questions,
One
comments?
question I had was like, I quite like your probabilistic detection design.
Yeah.
It's really cool. Like, hasn't been written about enough. And like, I wonder like a variation of that uses something like MPC or FHE, right? Like in the sense of computing over the private index of the data. Have you explored that? Have you thought about that?
So basically, okay, so I can like give a bit more context to everybody else about like how this system works. It's very cool. Yeah, so the idea is like you want to, instead of having to like scan this like giant fire hose of everybody else's state updates, you want to have less stuff to scan, but you don't want to give out to some server, here's like my exact transaction metadata. And so what you want is a probabilistic detection system that will detect all of your transactions, guaranteed, and will also detect a bunch of false positives. So you're basically taking this like fire hose, like tapping off a garden hose worth of stuff, and the thing you want is in there. And the way that works is you use a bit encryption scheme, like a asymmetric crypto bit encryption scheme. And you have, when someone sends you a transaction, they're going to encrypt K1 bits to like each to this like vector of public keys that you've published. And your detection key then is the vector of the secret keys for this bit encryption system. And when you hand out those that set of detection keys to some server, they can trial decrypt these K bits. And in the event that they were using the right key, they'll get all ones. But if that clue was not intended for you, when they use your detection key to examine the clue,
It's like the old school, like before we had RSA. Do you remember
yeah,
the crypto system whereby you, instead of like doing public key crypto, you would generate like a bunch of symmetric keys, and then you would like choose like two of them, and then you would combine them and like encrypt some piece of data and send it to someone. And it was like the other person was able to find out without like having an understanding of, you know, which keys you've chosen, like a man in the middle, for example. But yeah.
so it's basic. It's a quite neat. It's sort of like an encrypted Bloom filter.
Yeah.
But you need somebody to actually be like running the scanner for you, and the thing that you want to avoid is if they take your detection key. If some adversary basically is like collecting a substantial fraction of all the detection keys in the system, then if they, instead of just having a probabilistic view into your account, they have a probabilistic view into like your account and their account and their account and their account, they can piece together the information to reconstruct metadata, which is undesirable. So putting that detector in a TE can kind of remove that threat.